Hello everyone. Today I want to introduce our project BOWASP, Image Classification and Visualization in Deep Learning Network, next. This is our three parts of our project: introduction, experiments in classification and visualization in CNN. Next, please. The first part is our introduction. Our data is from Cargo Competition, BOWASP, Cargo. It has about 11 images in the dataset, and there are 4 classes to classify: bee, wasp, other insects, and non-insect. And we split the data to training data and validation data. The training data is about 70% of the original data. Next, please.
Okay, here we start training. In this section, we use several popular convolutional neural networks: ResNet-50, ResNet-34, VGG16, Inception V3, DenseNet-121, and GoogleNet. Due to the poor machine on hand and time limitation, we choose the pre-trained models. In PyTorch, some small changes in network structure, and we have trained every network with only 20 epochs. There are some basic ideas for networks. First is ResNet. The increase in the number of network layers is generally accompanied by the following problems: the consumption of computing resources. The model is prone to overfitting and the gradient vanishing, exploding problems. It's really a clever network, which makes it possible that we can do training on a very deep structure. The author explicitly let these stacked layers fit a residual mapping, which is assumed to be easier for optimization. The next is VGG. It is modified from AlexNet, use consecutive 3x3 convolution kernels to replace the larger convolution kernels, which means it increases the depth of the network to ensure more complex learning, and the cost is relatively small. In this project, we modify the 4 connected layers in the sequential process because we do not need so many parameters for our dataset. The next is Inception. This is the main convolution of Inception V3. It uses RMS probe optimizer, factorized 7x7 convolution. The first figure is 5x5 convolution is replaced by 2 3x3 convolution deeper. And the second figure is Inception modules after the factorization of the n/n convolutions, and the third figure is Inception modules with expanded the filter bank outputs. The next is DenseNet. Its basic idea is the same as ResNet, but it establishes a dense connection between all the front layers and the back layers, and its name comes from this. Another major feature of DenseNet is to realize feature reuse, which is called feature reuse through the connection of features on the channel. The last one is GoogleNet. Its idea is based on the Inception architecture. And the improved Inception architecture is shown in Figure 1. Gradient vanish is a common problem in all deep networks. So SIGD added auxiliary classifiers to assist the training and accelerate the network convergence. Finally, in order to reduce the parameters, the fully connected layer was also canceled. Here we will analyze the training results of these modules. All the conditions are the same except for models. The learning rate schedule is shown in the figure. This is the result of training and validation. In the training process, although Google Native's loss decreases the most fast at the beginning, VGG16 has the highest accuracy, which while there is a little different during the validation, because although DenseNet has the lowest loss, the models have highest accuracy are Inception V3 and VGG16. This is the final result on the test dataset. It is clear that VGG16 has the highest accuracy, which is about 95.69%, while Google Native's accuracy is the lowest.
And here I want to introduce our smallest sample of image dataset. To get a high classification accuracy for image, we use too much time for model training as before. Keeping a high accuracy, can we decrease computation time by sampling a little percent of images? The answer is yes. And here we use the technology for implementation, Fast AI. As you can see, the left figure is the layered architecture of Fast AI. This is a deep learning library that provides protections with high-level components that can quickly and easily provide state-of-the-art results. It also provides researchers with low-level components that can be mixed and matched to build new approaches. This project uses Fast AI for image data loading, model loading, and model training. And this is our loss change by the learning rate. As you can see, the loss change by Fast AI gives a suggesting learning rate for us to consider. Next, please. And here is our result of the smallest sample of image dataset. As you can see in the left figure, 4% is the smallest example that can make the classification accuracy keep at least 90%. And 3% of the image dataset is the smallest example that can make the classification accuracy keep at least 80%. And here I can conclude that if you want to require a 90% classification accuracy result, we can use just the 4% sample of the image dataset, and the computation times becomes 25 times faster. Next, please.
In the visualization in CNN part, we mainly use 2 pixel level explanation methods to deal with the task, salinity map and grid cam. The salinity map is a way to visualize the gradients of all pixels with highlighting the pixels that influence the class score most. And there are 2 kinds of maps. Next. In 1998, salinity map was introduced in the visual attention system, and the structure of the system is shown. Next. The computation of salinity map is the gradient of that Z in logit vector to the pixels. After computing the gradient, absolute values are taken to get the result. Next. In our project, we choose to show the salinity maps during the training process as the learning procedure. From the images, we can find that in early steps of training, the salinity map are more scattered, and in the last 2 images, the salinity map more concentrates on the target. Next. We also use the grid cam method to deal with the task. Grid cam is introduced in 2017 as an improvement of the previous cam method. The basic idea of the grid cam is to use the target concept gradient flowing to the last convolutional layer to produce a highlighting map, highlighting the target area. There are 2 characteristics of the model. First, it is really convenient to be used in any CNN models with full connect layers, such as ResNet 50 and VGG models. And compared with the previous method, there is no need to change the structure of the model or retrain the model. retrained model. We show an example in our project. This is the model of the GridCam. You can see the method acts on the last convolutional layer. And with linear combination, the result map is computed. Next. In this slide, more details are shown. The gradient of depth C to the feature maps is computed, and global pooling is conducted to get a mean value. The value stands for the importance of the feature maps. Next, the linear combination of feature maps with their importance as weight is computed, and ReLU function also acts on this step in order to get the final GridCam result. The visualization process is shown below. The heat maps is shown as the mask to the original images in order to show the difference more clearly. Next, in MSBD50 models, 2046 feature maps are used, so the same number of heat maps are computed. Several of them are shown here. Next, we show some other results computed in our project. You can see that the model performs quite well on the classification task. It mainly concentrates on the target, not the background or other objects, such as flowers. Next, GridCam method does well in this task, but details are not shown enough. The guided GridCam method, which is the combination of guided backpropagation and GridCam, is used, and images are shown here. There are more details and more focus on the targets in the guided GridCam maps. Next. This is the end of our presentation. Thank you for your listening.